Yeah. Now, that's not a universal.
On the other side, it would be a negative percentage, like it would be negative.
It would
add
say,
to the first
yeah, what would the wording be? It would say, what's the probability of being less than this percent?
No, it could still be,
Yeah, the key word in there is at least, so it has to be more than that.
Because the least is.
Yeah. All right,
No,
so,
could-
and it,
I mean, if, let's just say for argument's sake, towards the left side, you had one presented. The question would read, what's the probability that the stock had a return of at least 1%?
it would be, the question would read, there is a 1% chance that the stock had a return of less than what percent?
Right, I'm saying 1% as in the annual return percentage. So,
They're asking us to calculate the annual return percentage. They're not giving us the annual percentage. What they're giving us is the area under the curve. It may make more sense when I put this next point up. If this is 5% of the area, 5%, what percentage of the area, the points, the outcomes are less than that point?
95.
95. All right. So we now know we are looking for a z-score and a data point that has 95% of the data less than that data point. So we know how to find a z-score with 95% of the data below that z-score. We look right on the table, but this time we need to look in the center of the table for 0.95. When you find it, put your finger on it, look to the outside. What z-score gives us that area under the curve?
1.64.
How much?
Yeah, 1.65.
I like 1.65. What do you like, Aline? 164?
64 or 65.
64 or 65? I like the more extreme z-score. 1.6. If you have a choice between 1.64 and 1.65, I choose the bigger one, the one further from 0. Alright, so if you look on the z-table, you see 1.65 as the z-score that has 95% of the data less than that z-score, 5% of the data above, at least above that z-score. That makes sense? Wendy?
So it's 1.65.
So you look, where's your z-table? Yeah, so look right and look for 0.95, yeah.
So you
No, just look for 0.95. Yeah, so you don't even know that that exists yet. So you're like, oh, that's what I'm looking for. Alright, what z-score is associated with that? Yeah, 1.65.
Oh, okay.
Alright, so we're given 95% because we think for a minute about the wording of the question, even though it's confusing, but we've got it. 95% below. We now know that that has a z-score of 1.65. Remaining question is, what return has a z-score of 1.65? So let's take our z-score formula. 1.65 equals x percent minus 5.1 divided by 2.2,
look at this bullshit.
right? That's the equation, and we have one unknown factor. We do some algebra. Did I put the wrong number? What happened? No, you put the wrong one. No, she meant. And it turns out that this percentage return is what? 8.73%. Who said that? Good job.
what do you got?
But you get D now.
Oh, that's right. We have one more to do. Alex said I'm like, yes, you made it through that one. Oh, wait, no, we have another one.
So what do you get, x minus 0.05?
You have to multiply by to do Z and then add.
What?
Because you're gonna do the opposite to here less.
5, I did 0.051.
So here, right? So
I'm
this
leaving
is-
it
so
like
this
this.
is 5.1 over 2.
Okay,
So you cancel out the. Yes.
What was the same? Or. So 6.1 is a full
Right, I
stop.
understand.
Should we do this very last one? Yeah? Alright, so for the very last one, it's that same kind of work backwards type of deal. We are going to be given a percentage area under the curve. We will then need to find the z-score associated with that, and then need to find the actual point of data. So there's a 25% probability that the stock had a 5-year annual average return of less than what percent? So it's asking us for this percent, and there's a 25% chance that the stock had a return of less than that. So we're now looking for a 25% section. It's either this 25%, this 25%, or somewhere in the middle. Can you tell me which 25% section we are looking for?
Maybe it's
Less
Yeah, I like less than is this way. So this 25% here, so make it a little bigger, so we don't get confused. So we're looking for this 25% tail. Alright, and this is the cutoff point. Right, anything below a data point of this or z-score of this is 25% of the possible outcomes. And now we know there's a 25% probability to stock at 5-year annual return of less than this. What is this percentage?
7.
Okay. Alright, okay, so we know the area under the curve is 25%, right? We know that. What z-value has 25% of the data below it?
0.68?
0.68? I think it's going to be a negative z-score.
Yeah, that's what I'm trying to figure out.
Would you veer towards closer or, so it's like, would it,
Same
because
percent.
there's
That's below 25.
0.6.
Oh, yeah, the one further from 0.
So it would be
Minus whatever.
You don't have one.
0.68.
This one, it's in the book.
Negative 0.68. Okay. Okay, I could get on board with that. Negative 0.68. So if you have a negative z-table, you look right for the part in the middle that says 0.25. Now if you don't, you have to do a 1 minus deal. It's not a problem. You would look on the positive side for 0.75, right?
5.8.
Yeah, 0.75, you put your finger on 0.75, you would look on the edges, you would see it would be 6.8, and you would know that that would be a negative because you're looking for the opposite tail. So is everyone okay with how we got negative 0.68 as the z-score for this unknown return?
So we're looking for where number? No one is.
It's on the negative side.
Oh, sure.
You have to have the negative chart.
Right.
Alright, so then once we're comfortable with the negative 0.68 z-score, we just plug that into our z-score formula. Negative 0.68 equals the unknown return minus the mean divided by the standard deviation. You solve for this and you get, I heard someone say it earlier. I would shine on it.
4.79.
Huh.
I got 6.
I don't know if I like that.
3.6.
Yeah, I like 3.6 better.
I got 3.6.
3.6,
3.04.
0%, okay? Are we in agreement there?
Do you mind working that algebra out?
Working this algebra out?
Yeah, like
Yeah, it's
I
gonna give me a
had
headache.
algebra for 40 years.
He said it's gonna be nice.
We can do cross multiplying after class if you want.
Okay.
For now, just know if we put in 3.6 here,
It'll
will-
come out to.
it will come out to the even equation. Any questions there? 22 part D.
You don't know how to do it.
I'm stuck on the cross multiplication.
Yeah, you need to at least.
Challenge my algebra skills here.
You don't know
That
it?
challenge, you don't know.
Alright, so we have an equation with one unknown. We have this in the denominator, so what we do first is we multiply both sides by 2.2. So if we multiply this side by 2.2, it cancels. So we multiply this by 2.2. Alright, what do we get 2.2 times negative 6.8?
Negative 1.496.
496 equals X percentage minus 5.1. So
Then you have to add.
Plus 5.1.
Bring
The
the
5.1
plus
to the
5.1
left.
on both sides.
plus 5.1
Right.
plus 5.1. Alright, so what's negative 0.496 plus 5.1?
3.6.
3.60 equals X percent. What do you think, Carol? Not bad, huh?
See, motherfuckers don't do that shit. Yeah. What?
Went to a good class.
All right.
Wait, don't.
Alright, are we ready to estimate a population mean?
Yeah, we should have.
Yeah, so that work we've done with the normal distribution, that will be extremely helpful in this class and in future classes, of course. It's just the foundation. I feel like you've got a good handle on it, and we'll get plenty of chance to practice it going forward. So tonight we will estimate a population mean, for example, average income. In order to do that, we want the average income in, say, New York City, 8.5 million people. We can't ask everyone, we have to sample. Well, how do we sample? We use good sampling techniques, and we'll use what's called statistical inference. This just means we take a sample and we infer things from the sample. We'll learn this really cool concept called the sampling distribution and the sample mean. which will give us an indication of how confident we can be that our sample is accurate. And that will in turn give us confidence intervals. So when we have a sample mean for income in New York City of, say, 74,000, we will have a confidence interval. We will say, I think the average income in the whole population, i.e. New York City, is between 71 and 77. And we'll say what percentage confident we are because of things we will learn about this sampling distribution and sample mean, which is all stuff that you know already, which is based on the normal distribution. So, estimating a population mean, I already gave the example. What is the average salary in this town? For example, you might also need to know things like how much money do teenagers spend on video games? If they spend a lot, maybe you should invest in your new product. What is the average error rate in my production process? What is the average number of coin flips that come up heads out of 20 coin flips? We'll revisit that example to illustrate a point. As I mentioned, statistical inference, do not get scared by that term. It just means we take a sample and we infer something about the whole population based on that sample. So here's our population. We sample a little subset of that population, crunch the numbers, and then we say, now I think something about the rest of that population. I think that sample can tell me something about everyone in that population. Statistical inference. And why do we sample? Well, if we want to know the average income in New York City, it's going to be very, very difficult to ask all 9 million people. I mean, imagine trying to do that. We have to hire thousands of unemployed people, college kids, give them clipboards, give them a section, walk out to this neighborhood, knock on everybody's door, or even trying to call that many people would be difficult. Those college kids who are knocking on the doors, they get the door slammed in their face a few times, then they're like, I don't want to do this anymore, I just want to sit in the car and play video games, I'll make up some numbers. You do not want that situation. Instead, you want a team of highly trained professionals calling a small number of people, a small sample, and asking them questions in a way that is objective, that's not going to lead to wrong data. And you can use sampling techniques to indicate how confident you can be about a relatively small sample. Now, we're going to use, when we sample, a process called simple random sampling, which just means everything is based on random probabilities. So if you want to know income, you don't just sit in at the bus stop and say, how much money do you make to the first 200 people you see? You're going to get people who are at the bus station, so maybe they have less money. It's going to skew your data for that reason. Similarly, you don't go to the golf course and ask the first 100 people you see, how much money do you make? That's also going to skew your sample data. Now you know that just from common sense. You're asking the wrong population to get an accurate number. But you also, this may ring a bell, you also want your sample to be based on complete random probability. Remember, we talked about the normal distribution being based on that random probability? Well, it turns out that we can use that to our advantage when we sample. If and only if our sample is based on a complete random distribution. Ideally, you might have every single member of your population listed in, say, an Excel spreadsheet, and you could assign them all a random number and select the top 200 random numbers, and those would be the people in your sample. Simple random sample simply means every combination of n members, n, little n is the sample size, has equal opportunity of being in your sample. Now, I mentioned how we could use the normal distribution to our advantage and what we know about that. Let me remind you just a couple things you know about normally distributed data. if data is normally distributed, you know it will have the center around the mean, which will also be the median and the mode. And within one standard deviation of that mean, you will find 68.3% of the data. Perhaps 68.3% of residents in New York City make between one standard deviation of the mean. You also know that if you go out to 2 standard deviations, 95.5% of the points of data will be within that interval. You know those 2 things, you know everything in between because you have a z-table. You can look up exactly how much of the data will be within a certain number of standard deviations. And we'll keep that in mind, because remember I mentioned that we're going to be able to use this to our advantage when we sample. So let's revisit this example to make a point. Remember this coin flip example? We're going to flip a coin 20 times, and we're going to see how many times it comes up heads. And we calculated this. We know how it works. We know the probability of flipping a coin 20 times and it coming up heads 8 times. What is that? About 14%, right?
Closer to 12, yeah.
Yes, thank you. All right, so we know the probabilities of all of those outcomes because we calculated them. And what I want to do with this is I want to do a thought experiment. So we're the ones who know this outcome. We know this distribution. But let's find some researchers who do not know this distribution, and let's give them an assignment. All right, so some researchers next door who don't have access to this graph. Let's tell them about this coin flip experiment. Let's say, go to each and every student in Mercy College, have them do this experiment. Flip a coin 20 times, write down the number of times it comes up heads. And then I want you to calculate the mean number of coin flips that come up heads. All right, so this group of researchers who is outside of this room, they don't know what we know. They've gone to 10,000 Mercy College students. They said, hey, go home tonight, flip a coin 20 times, write down the number of times it comes up heads. Okay, so they have a population of 10,000 Mercy College students. All right, and then they come back and like, all right, we told everyone to do that, and they wrote down the number of times that came up heads. And now we tell them, okay, I want you to find the mean number of heads in that population. All right, what is the mean? So you remember this symbol, mu?
Yeah.
All right, what does it mean specifically?
Average.
It means average, it means population mean. All right, so this is the population mean of all 10,000 Mercy College students. Now, since we have access to this graph and they don't, what is this? Let's talk softly. What is this? What's the answer? What is the population mean of this graph?
17.5.
10.
It's in between.
We're getting 17.5.
Go to 10,
It's 10.
and then you go up.
It's 10.
That's 10.
It's 10. All right, that is the average number of coin flips that will come up heads. Now, a lot of these 10,000 Mercy College students, they'll actually get 10 coin flips. Some of them may get a few more, some of them may get a few less. But there's equal probability getting a few more is getting a few less, so these folks will cancel out. And then we'll have somebody who gets super lucky and get like 16 coin flips, somebody who gets super unlucky and get only 4 heads. Those 2 people will average out, because we've got 10,000 people. So the graph in reality is going to look a lot like this. And let's just say the population mean, the true population mean, is 10. We know that. But do our researchers know that?
No.
They do not know that. So they're going to find a sample mean. This little X bar, sample mean. Let me ask you something. What is the most likely outcome for their sample mean?
It's gonna be a slightly higher number. Is it?
Okay, you say slightly higher. We'll come back to you on that. I want to know why you think that. Anyone else have another guess?
10?
10. 10.
9, because you minus 1.
Yeah.
Did you say the sample size is 10,000?
Sample size is 10,000.
Oh, sorry.
It's all good?
The correct answer is 10. Why did you think maybe more than 10?
I probably remember something from last week and I misused that information.
Okay, well the reason I follow up on that is because maybe you're suggesting that there might be a skew in the way this data is presented.
Correct.
All right, maybe Mercy College students may be embarrassed that they didn't get enough heads, so they may write higher numbers,
Yeah.
something like that.
Or probably not the correct data exactly, but
So let's assume that that might be a reason that would skew the data, but let's say that's not happening.
okay.
All right, let's say these researchers, besides the fact they don't know this, they're using good researching techniques. They're saying it's okay if you got 7 heads, it's all right, blah blah blah.
Good
Just
thing.
tell me the actual numbers. They're using good techniques, and the most likely outcome for their sample mean is going to be 10. Now it's not going to be exactly 10, because they're not going to have time, suppose, to ask all 10,000. They're going to have to ask a sample. Suppose they ask a sample of 30. Remember little n equals 30? And it's not actually going to, it's most likely would be 10, but it's probably not going to come out to be exactly 10. Maybe it's going to be 10.2. I have a couple of questions for you. Those researchers outside this room who got a sample mean of 10.2, how confident could they be that this sample mean is accurate? And by accurate, I mean that this sample mean is close to the true population mean. How confident would they be that they've got a good estimate for the true population mean?
Well, we know exactly as many flips a person we do and we have them. Well, we never know because they don't have the normal distribution table. We wouldn't know, I guess, but let's say that we perfectly calculate that and then compare it to the actual
Okay.
data.
Okay, so this is a good chance to just free form. There's no real right answer I'm going for here. So this is good, just sort of free form thought. 2 things I would like to draw to your attention. Well, first let me say, if they've only asked 30 people out of 10,000,
Oh,
we might be a little concerned. They might be a little concerned. They're like, well, it's only 30 people out of 10,000. I don't know if we've really got a good representation with our sample mean to say that we are all close to the true population mean. Let me just erase this 10 for a while. We'll just have to remember in our head that we know what it is. But as far as they're concerned, it's a question mark. So they only have a sample size of 30. So we've got that like on the not very confident side. Let me bring up a couple of points which would put it on the yes, we are confident that we have a good estimate side. Let me ask you first this question. These researchers, what is the probability that any one person they ask flipped the coin 10 times? Flipped the coin heads 10 times? Yeah, they flipped the coin 20 times and got 10 heads, sorry. What is the chance that any one student, any one of their 30 students, wrote down 10 on that piece of paper?
be slightly low. Very low.
It's a number, what is it?
So 17?
17%, okay? What are the probability that any student got, flipped the coin 20 times and got it 9, 10, or 11? Any of those 3?
16,
Less than 60.
Well, 16, 17%, so.
No, 15.
49. You add those together, right? You can say the chance of being in any of these 3, we add these 3 together, it comes out to about 49%. Okay, so any one of those 30 people, half of them, are going to say their answer was 9, 10, or 11. So are you now a little bit more convinced that maybe this sample mean is pretty accurate? Because half the people in your sample pool gave you a very close to the right number answer, right? And then we average them together, we might even get closer to the right answer. Let me bring up another point. Suppose one crazy student at Mercy College gets really lucky, flips the coin 20 times, and it comes up heads 15 of those times. What are the chances of that happening for that one student?
Less than 2%.
Yeah, less than 2%. By 1 point something percent. So that one Mercy College student, pretty lucky student, right? Chances of that happening very low. Second question. What are the chances that all 30 students in this sample pool flipped the coin 20 times and it came up heads 15 or more times?
Less than 2%.
Well, we start finding 2% of the 30, of 30. Find 2% of the 30, no?
Okay, so if I were to ask you again, the chance of one student flipping a coin and it coming up heads 15, 2%. What are the chances of all 30?
None.
Oh,
From the population or from the sample?
From the sample, all 30 in the sample. The chance of anyone in this sample, any one student in this sample, 15 or more heads, 2%. We know that.
Right.
What are the chances of every single student, all 30, of flipping the coin 15 or more times heads? 0 is close to 0. Alright, so is it less than 2% or
Yes.
it's less than 2%? Does anyone know how to calculate that? What you would do is you would take 2% to the 30th power. You would take 2% times 2% times 2%. The first time you take 2% times 2%, you get like 1/20th of 1%. And then you take it by 2%, you get 1 in 1,000. You take it by 2%, you get like 1 in a million. Then you take it by 2% again, you get 1 in a billion. And you keep going like that until the chances of all 30 people being 1 in a bazillion, gazillion, trillion. I made that up. So the chances of all 30 students in this sample pool being in this tail, very, very slim. Right? And it's the same thing down here. The chances of all 30 students flipping the coin and getting really unlucky, 5 or less heads, that's just one student. What about all 30 students being in this tail? 1 in a billion, gazillion, trillion. Not happening. So now, are you feeling a little bit more confident that this sample mean of 10 is pretty accurate? Our sample mean of 10.2 is pretty close to the right number? So now we know two things that we didn't think about before. One, any one student has a very good chance of being 9, 10, or 11. And then the chances of our sample, all 30 of our students averaging out to one of these tails or one of these tails, tiny, tiny percentage. Pretty much not happening. And the logic works the same way as we go in. Like the chances of our sample mean being 15 or more. So this is X bar being 15 or more. That's 1 in a billion gazillion. The chances of it being 14 or more. That's like 1 in a billion. The chances of 13 or more, 1 in a million. The chances of 12 and more, 1 in 100,000, I don't know, something like that. And then when we get into 9, 10, or 11, maybe we're like, okay, our sample mean could reasonably be there. But anything outside of that range, just not happening. And this out of a sample size of just 30. So it might surprise you to realize that if we want to know the average income in New York City, 8.5 million people, that we might be able to ask just 30 people and be reasonably confident that we've got a good sample. All right, it's a little scary, right? It doesn't have to be a large number. These are two steps in the rationale for why we could ask In a population of 8.5 million, just 30 people, and be pretty reasonably confident. Okay, so let's take a break, and when we come back, we'll extend this with a little more specifics. What time do we have now? 8:06? What do you want, like? 8:20? We say 8:20? Let's come back at 8:20.
Get all the 21 credits?
Of course. I mean, if somebody didn't get that, that was.
It was hilarious.
Yeah, they was just bullshit.
What other classes you taking?
I got this. I got operations management tomorrow. And I have no, that's actually Tuesday, operations management. And I have business communications class. I don't even, I'll tell you right now.
Communication process.
Communication classes.
Nice.
Yeah. So that's pretty, this is all pretty, standard. This is just right. But everything else is just more like PowerPoints and, presentations.
This is just all.
This is all the mathematical stuff.
Some random kid just did it.
No, why you
What are you talking about? I'm even confused. You want to? I said, come on.
What classes you take?
You got issues.
Communication process and just doing two.
Okay. You taking it here too, or?
Both here, Mondays, Wednesdays. Yeah.
Who's driving the Dunkin' Donuts?
Who's the professor for that?
Zarelli. Mike Zarelli.
Trying to see if that's the same. Oh, no, that's Jason Pacelli. Jason Pacelli.
Jason, ball guy.
Ball head.
Young.
Yeah, Philly, young. Yeah, he's cool. It's a small class. I think there's only like 10 of us.
Yeah, there's like 5 people from our turbo in the communication class.
Oh,
It's funny.
yeah, I got in the operations management, it's like 3 of us.
It's fun to see everybody.
Yeah, you're gonna see him periodically.
Scattered everywhere.
Yeah, because some is in Manhattan.
And over there. Is it on? Intro. Okay. 751, this class, and managerial. Chris, you went to work today? You called out for that?
Huh?
You called out?
No, I had like a day off I could use.
End of the year, right? Use it up. Use it.
I'm going. It's a terrible day, though. I'm sorry, I gotta pick up on my jump. It's right there when you get to the end.
Oh, you said it's like only 3 to 5.
Yeah.
I didn't have to book yet, so I was like, I'll
You
wait
gotta do
till.
all the Excel assignments and turn them in on the blackboard. Yeah. Get the syllabus. You was ahead of Thursday.
I got the syllabus. I saw it online. I did the first quiz. You do the first quiz.
Yeah.
Um,
And then I'm just gonna do the quiz in the Excel and submit it on Blackboard.
They all do the quiz,
you
right?
did a quiz on Excel.
No, the quiz is the Excel is separate. Now I wish I could show you on the computer. It's separate when you click on Blackboard. I go to
And the Excel is just for the assignments, not the
It's
quizzes.
just the assignments, not for the quiz. basically you wanna see how we know how to do the, work the Excel and work the problems out. But in the book, it gives you, see, like it gives you,
Yeah, I didn't do the
see,
first assignments yet.
yeah, he said you do, see, it gives you a step by step. When you do the Excel, it tells you like what to go to, what to press next. It's basically step by step. It'll
Yeah.
walk you through it. Click that, do that, do all of, you know what I'm saying?
Yep.
But for some reason, I got to like phase 2 of that shit, and that shit didn't work out right.
No?
Yeah, I'm gonna have to do it again, but he said he let it do it again and resubmit it.
Cool.
And then
Trying
all
to
the
catch
quizzes,
up on everything
yeah,
this
all the
weekend.
quizzes he take for the final, he take questions from the quiz.
Oh, cool.
Yeah, so just memorize, basically remember some of them questions.
We're not doing it here. We don't have to come to class for the final.
What, for the final?
Yeah.
The final's here?
No, I said we don't have to come.
Oh, for the
On the
final?
syllabus, it says don't come to class, just take it whenever.
Oh, it's gonna be online?
Yeah, on
Oh,
Blackboard.
shit, I ain't even, that's crazy though.
It's great. We'll take it all together.
Yeah.
I already told 2 people, I'm like, hey, my final, I'm gonna need you. And they're like, yeah. I'll be like, I'll buy you beers and dinner after.
Right, all that, right? You already know.
I was like, come on.
Yeah.
And they're like, okay. So I feel like I'm good for that.
Yeah, that's super cool.
Yeah. Beers and dinner. Help me with my final.
That's right.
These
Matter of
guys-
fact, we had a biz dinner while you doing this shit. Shit.
So you guys are doing like every paper on
I was just with Powers.
Oh, yeah?
Yeah, we were at an open house tonight, graduate open house.
Okay.
And he was there for MBA.
Right.
Guy's the man.
Nah, yeah, he's super cool. Super cool.
But there were, I don't know, if it's somebody, 2 guys that weren't there, and somebody sent me a message, like, oh no, you hearing them. So I don't know who he is, but I have been there. Thanks. So I said to myself, I'm gonna wait for the first thing next week, and I'm gonna see how it goes. And after that, I'm gonna speak to them if it doesn't work out. And then that's the thing, when I'm going to leave, it wants to see you, you're not gonna go to the bump. No, I'm not gonna be responsible for other people.
Register for this one? Anything?
I just registered now. 704. I'm taking the management course.
Oh, yeah.
One of the other girls in the other class, she's taking it, and I had asked originally. But she said that, like, she doesn't have any voice. Oh, really? She said, but the professor said, like, the homework assignment, don't bring it to the book. She was like, so I'm a little confused. You see, there's pros and cons for both.
Not bad.
There's pros and cons. Well, I feel like now, I'm feeling like I'm gonna like that idea. When I went to, I just started to see the options. Is it a good thing? Yeah, all my options there, people go for That's what I did, and then, because one of my other friends,
Just take more writing. Yeah.
it's like, no, board.
A lot of the reading was okay. The reading is fun. Except for the one with the weather, climate change, Kyoto, with all the theme mechanism. Yeah. I told her, I was like, oh, it's so time consuming. I had to read it like 2 or 3 times, flipping back and forth. What is the acronym?
You have someone who organized something. So far, it seems to be good, because she already had her stuff. She was like, here's my paper,
Yeah.
look it over.
That's the one. It's a clean.
That was it, yeah. Everyone was complaining about that.
I have one group member
Not a
that
good reading. Reading 2 or 3 times.
Yeah, I read that one.
he did it, and then the one girl who brought it.
Take it into consideration.
Still going tomorrow.
Yeah.
That's perfect.
I'm trying not to hit it.
God can write it, because
For real, I mean, I have to catch it. I mean, stretch me.
I have it too. I didn't get a chance to read it until I was doing my weekend. But he's like, hey, you know, everybody should be so that we can go over it tomorrow. So we can get a chance to write it. Like, iffy. He's like, who knows?
Oh, you didn't submit it? No, I submitted it.
So then he's like, it's not the book, but everybody thinks like it is. And she's like, oh wow, look at that. And he's like, I think it was under $20. Oh, it's individual? And he's like, oh, okay, I don't have it yet. I'll try. I'll try. Oh, you can't try. Anything. That's the world.
Yeah. I don't know, it's just now. I read this the last minute. I was debating, should I take it, should I not?
I do that, Kelsey? My kid does salsa. Thank you. I gotta order myself a soul bath.
Yeah.
I love it. I would go shopping. I would go shopping. Don't do the website. It's
Yeah. we go
All right, I did promise 8:20, so let's go ahead and get started. Before the break, we talked about using this coin flip example. So we've got 10,000 Mercy College students. We've got a group of researchers who doesn't know how that binomial distribution works, so they don't have the right answers. And we've asked them to go find a true population mean. All right, so this mu out of all 10,000 Mercy College students. They come up with a sample mean, say it's 10.2, and we went over some reasons out of 30 people. They asked 30 Mercy College students sample because they couldn't ask all 10,000 of them. But we went over some reasons why they might be reasonably confident that they got the right answer. That this sample mean was really pretty close to the true population mean. One, any one of their 30 students would be pretty much 9, 10, or 11, would be 9, 10, or 11. And the chances of all 30 students being in one of those extreme tails, very, very unlikely. So now, then we extended that and said, guess what? If we want to know the average income in New York City, 8.5 million people, we could ask just 30 people. And for the same, based on the same logic, we would be surprisingly close to the true mean income of all 8.5 million people. Now we're going to look at the exact numbers and the exact confidence intervals that we could estimate based on sampling. So suppose you were to take a sample of 30 students, said how many times did your coin flip experiment come up heads? You write down that number, the first time you get 10.2. Suppose just in theory, you were to do that many, many times. So you take a sample of 30 students, calculate the mean, write it down, throw those 30 students back. Take another sample of 30 students, write down the mean, throw those students back. You do this over and over again, say 10,000 times. And you put those results on a frequency distribution. And we're going to call that frequency distribution the sampling distribution of the sample mean. Sampling distribution of the sample mean. Alright, so we've got the outcome on the horizontal axis. We've got the frequency on the vertical axis. So the first time we sample, it comes out to 10.2. So let's put a little x here, 10.2. Then we do it again. It comes out to say 9.7. We put a little x here, 9.7. We keep doing this over and over and over and over. And each time we get the same outcome that we've previously gotten, we stack the x on top of the other one. And we get a higher frequency of that particular outcome. So this is a frequency distribution. We're going to call it a sampling distribution. What is on this distribution? 10,000 different sample means. So that's why we'll call it the sampling distribution of the sample mean. Let me ask you some questions about this frequency distribution we just created. What would be the mean, median, and mode of this distribution? Yes, 10. Because 10 is the right answer. 10 is the population mean. So every time they sample, they're most likely to get the right answer. Sometimes they'll get a little higher, sometimes they'll get a little less, but on average, they're going to get the right answer, as long as they're using good sampling procedures. Mean, median, it would also be the most likely, it would be the average, it would be the most likely outcome, and if there's random probabilities, then there would be an equal number of higher sample means and an equal number of lower sample means, so the median would also be 10. What would this distribution look like? Normal. A bell curve. Why would it look like a bell curve?
The mean, median, and the mode are all in the center.
Mean, median, and mode are all in the center. Excellent. Yeah, I gave a hint that it was evenly distributed. I said equal probability being a little bit above the mean, a little bit below the mean. Equal probability, or equal probabilities of being a lot above the mean and a lot below the mean. Okay, so this is one of those things that would fall into a normally distributed pattern. Law of large numbers, complete random probability distribution. Would you assume that this distribution is normal? Yes, you would. Law of large numbers, complete random probability. How confident would you be that any one of your sample means would be within one standard deviation of the true population mean?
68.3, 95.
Yeah. So the center of this distribution is in fact the true population mean. Okay, that's the most likely outcome, that is the average outcome, and that is the median outcome. This is normally distributed, the reasons we just talked about. So within one standard deviation of any normally distributed frequency distribution lies 68.3% of the data. So you just took a sample mean, the researchers next door did, of 30 Mercy College students. They came up with a sample mean. We can now say with exact certainty the likelihood that that sample mean will be within one standard deviation of the right answer. Let me just repeat that because that's an important point. We just asked a group of researchers to take a sample of 30 students. They came up with a sample mean, and they can be 68.3% certain that their sample mean is within one standard deviation of the right answer. How confident can they be that their sample mean is within two standard deviations of the right answer? 95. So those researchers, they can stand up, present their results, and they can say, I'm 95.5% confident that this sample mean is within two standard deviations of the true population mean. They can say with exact precision. Last question. Do you think the standard deviation of this new distribution, this sampling distribution of the sample mean, do you think it would be,
Smaller, larger, or the same?
smaller, larger, or the same as that of the parent population? Now the parent population is all 10,000 students. Right, that was a frequency distribution that we saw with the coin flip thing.
Right.
Right, it would look like that. Do you think the standard deviation of this would be smaller, larger, or the same as the parent population?
Same.
All right. Check it out. This is the parent population, the population distribution of all 10,000 Mercy College students. This is the sampling distribution of the sample mean. The reason why this is skinnier, why it has a smaller standard deviation, is because, remember we went through that thought experiment? What's the probability of one student flipping a coin and it coming up heads 15 times? 2%? Okay, that's a pretty exceptional student, but it happens 2% of the time. I mean, we've all been that 2%, right? One student could be 2%. What are the chances of a group of 30 students being in that 2% range? Very small. Not happening. 1 in a billion gazillion. 2% raised to the 30th power. So the sampling distribution of the sample mean pretty much will not include that as a possible outcome. It will be possible, it will be a tiny, tiny possibility. But that outlier will not be on the sampling distribution of the sample mean, except in a very unlikely form. And as we go further and further in, the chances of these outliers ending up on the sampling distribution of the sample mean, not likely. So this frequency distribution has a smaller standard deviation. And guess what that means? Well, that means when they stand up and give their sample results and say, I'm 95.5% confident that my answer is within two standard deviations of the true population mean, they can give a pretty precise small standard deviation. And they can give a pretty exact confidence interval. So this is the sampling distribution of the sample mean.